So now I want to start with this simple design. It's basically just two arms that are thrust up. They're on motors, but the motors only go one direction. This one goes up, back. This one goes forward by hitting 9. So they just basically can come together. You can go in one direction. That's it. When this starts, these two springs are going to push this down and push the arms up, and then they'll be free to kind of just rotate back and forth. The only difference is this one has a steel chain. I lightened it up a little bit, so it's a light steel chain holding this wooden ball. It's all wooden. Not that it matters. It would all work the same. It's just wood's lighter. It doesn't have as much mass, and so therefore it's going to move a little bit quicker. So there's nothing. We can even make these metal if it makes you feel better. But again, let's make it light because I don't want 1.2. So really light metal. 1.2. So super light metal. Okay, no big deal. So we're going to hit start and just let it play out. Just watch what happens. So boom. Okay. So far I'm not putting any power into the arms. So they're just kind of doing their thing. I just want this to kind of let it resolve itself. All right, I don't want to get these things caught up. I want to see if I can figure out a strategy to see if I can't get myself moving here. Just from playing with this, I know I'm gonna try to drive it with the light one and use that against the heavy one. So the light one is 8. Yeah. So okay. So if I just little wax. Okay. So what we're trying to do, well, I think it's already over. Yeah. Okay, so what I'm trying to do is get out of my position in space, and I think I just did. All right, let's go back a little bit. All right, so let's get rid of the dirt. All right. Let's make sure everything is stopped. Velocities 0. Everybody's frozen. Momentum. Boom. Okay. Play it out. So that's good. Okay. So yeah, I'm not sure how that's going back into position, folks. So clearly this has to be a problem with the program because, you can't just float out of your position in space like that. I mean, the conservation of energy means that this has to go back. But there's a problem with that because this algodo is actually, let's see. I mean, granted, it doesn't have a very fast clock, um, um, but we're not really doing anything that requires any. Let's see. Yeah, it takes the Lagrangian, which means it's just looking at the energy from one moment to the next. So boom, let's go back. Let's try it again. Okay, off it goes. And again, we're not putting anything. We didn't do anything to it. This just was literally doing itself. We're going to add a bunch of stuff here. See if we can get it go a little bit faster. So So what's going on? So why is this thing um, going out of its frame of reference? It seems like we're now flying through space. How is that possible? Let's wait for this one to kind of resolve, right? But you're going to see, okay, you're not stopping this thing. All right, so let's see if we can't just amp it up a little bit. Oof. Oop. Oh, I messed it up. Well, if you break it, I guess it can, like, but no pieces flew off, so we didn't lose any mass, right? Oh, that's not looking good. Interesting. So when those come together, oh yeah, this is, and now just whoop, see what happens. See, now we're out of our, see, there's no way you're putting that back. All right, so boom, little goop, little kick, yeah, little kick, 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 little kick, little kick, kick, little kick, and see what happens. Boom. Nice. Yeah. Again, I don't really know what's going on, but see. I don't see you putting the system back into position now. It just doesn't seem possible to me. I mean, obviously, to somebody who knows physics, they'll be able to tell you that eventually maybe that will go back around. But then all I got to do is, since our system has been kind of reset in a different. Oh, there we go. Oh, snap! Right, give another whack. You understand? I have no idea how to drive this thing. Like, I know I can change directions and do things and make it work, but I just don't know. Like, I think, I don't know. I don't want to talk about what I think. It's just look at what you can see, right? I wish there was more contact with the other. There we go. Just smack them together. Oop. And now it's terrible. I think it's broken. Yeah, so got some wraparound. So it looks like it's just going to spin around this, but then if I give a little bit of a, I get it off there. Now it's broken now. Set it right on top there, so it looks cool. Nope. Broken. These things are lodged. They ain't hitting the button. Not doing anything. No translation of force. Anyway. Try another one. All right, let's say a little bit of weight to that ball. See if that has any impact. Douche. A bit of a kick. Dun, dun, dun. Oof. That's a good one. Okay, and whack. I like when it swings around and hits, like, that just tells, like, and again, that might not be anything, but it feels like when it hits the other side, it's doing something profound. Probably not. And roll around. I know this is boring, but this is kind of what you have to do to test this stuff out and see what it's doing, why it's doing it. Right? This angle of force here, as it's being played out here, like how is this, like you can see where, that's why I like using the chain, because you can actually see where the force lanes are without actually turning everything on. Right? So you can, few momentums. Let's see. Okay, so you can see the momentums of where everything's going, right? You can also see like this is moving in that direction, this is coming here, and they're going to kind of collide. Right, so it's going to like spin around and down into here, it looks like. And then so like what happens when I put a little bit of juice in here, this is going to shoot straight up. Right, let's go real slow. Let's go real slow. Right, so I'm going to put a little bit of juice into, see, now it's coming up a little bit. It's going to smack that ball. Kadoosh. Right, which is going to make this thing move back. And this thing is now going to go, in this direction. Sort of. It's going to it's going to get a torque. And you can do the math. I mean, you got all the angles are right here, and all the like the force, and you can see where everything is. So you can do the math and figure out, okay. So say you think this program is messed up, that it's just not right. You know what I mean? Say like you think the speed of the program is it's just allowing for all these uh, anomalies. Um, you know, it's not really the case because that's not what the math is telling you. So I mean, you can actually just do the math on this from these angles and figure out where everything's going to go. This is not a complicated setup. I mean, it is. I mean, you do have a lot of different moving parts, but you can tell you've got the math right here. You know what I mean? So, and you can see the direction of forces. Um, like everything in here is like, let's see, let's select everything, pause it for a second. As if you hit it the wrong way, it gets a little screwy. Can I just do information? Just want to look at the information. There we go. Information. There we go. So I mean, you got the mass, you got the moment of inertia, the impulse on the different axles, your current momentum. This is how you get your Lagrangians. You could do a Hamiltonian and a Lagrangian, even though I'm not going to tell you anything different. But you have all the information right here, so you can do all of this instantaneously just by looking at these angles. I mean, I'm not going to do it for you because I mean, I don't doubt that it works. I've already done all the math, but for myself, but if you're going to argue that this thing isn't functioning properly, well, I mean, it's doing math, advancing, doing math, advancing, doing math, advancing. I mean, it's functioning properly, at least as far as I understand. So if this thing should drift out of its frame of reference, it's not because the program's wrong or the math is wrong. You can do the math. You can see that there's no. I mean, look at the direction of forces. If you do a vector analysis, you take all of these vectors, right? All of these forces and all of this stuff, and you figure out from this, like this is how you, if you want to understand Noether, right? Like if you want to understand, the laws of conservation of energy, what they're saying at its very core is simple. I have this paused. Now we have been playing this scenario out, right? It had been running a while, and we stopped it. Now, from the moment I stopped it, there's certain things that will not change. This isn't going to just turn into a magic wand and fly off. I mean, I can change it into something else. I can change the mass, I could do whatever, but if I do that, if I change the density, if I change anything, I mean, not so much the friction, but I mean, like if I change the density, I'm changing the whole equation. So by getting rid of mass, whether I throw it off of here or not, I'm going to change the equation. Okay, so we're not, that's something that's an invariant. It can't change from one moment to the next. I mean, you can, but you're just cheating the system. That's breaking it. So if we know that this wood's mass will be exactly what it was, if I hit boom, okay, so the mass has not changed. If I look at the material, the mass is still the exact 0.8889, right? I'm going to hit it again, stop. Mass has not changed. It can't change. The friction can't change. So from 1 second to the next, from one moment to the next, all this mass has to stay the same. And the direction of forces have got to evolve from one moment to the next. That is also an invariant, which means your linear motion, if it's traveling in this direction, if this line is saying it's traveling in this direction, it will continue. When I hit play again, it's going to move in that direction. It has to. That is the laws of the conservation of energy and momentum wrapped up in one. If this line is saying I'm going in that direction, boom, I go in that direction. Not difficult, right? And this angle is the direction that I'm going off of, like, I don't know, like the system center, right? So I'm being pulled in this direction from the center of mass of this system. So um, you can do all of this and figure out why it's working. And there's certain things that cannot change, and there's certain things that will change. And that's where Emmy Noether comes in, and she says, that these things lead to conservation laws. So when we're looking at this stuff, these are the conservation laws in action, right? This program itself, this algodo, right? They use the Lagrangian mechanics to figure out from this moment to the next, where is this going to be? And it's not hard to do. You can see the line. It's not hard to do. This thing right now is just apparently spinning around. Now, if I add a little bit of energy into the system via this torque here, right? Boom. That's how it plays out. You have to account for how this system is constructed when you do that. So I'm going to hit it again, right? So now every time energy is introduced here, it has to play out. And what's interesting is even though I'm putting a torque on the system, this nonsense over here allows me to translate that into not direct linear thrust, because it doesn't really work that way, but there's a thrust when this thing acts screwy. So, I kick it up, I do that, it's going to, like here, it's going to wrap around, boom, kicks in the bottom. Now, I know you're saying, well, okay, it's the equal and opposite reaction, and it is. There is an equal and opposite reaction. But there's several of them. So the first equal and opposite reaction is when I fired this thing off in the first place, right? So there's an equal and opposite reaction. And now this thing is responding to that initial action chaotically compared to what this can do. Like this can't respond the same way, so now you're getting this weird, we've kind of reassembled the center of mass around this particular point, right? Because this is heavy, this chain is heavy, right? And so this thing is just spinning around here now. But every time we do that, we're changing where this thing is allowed to spin around. So you spin around this way, and then once you change a little bit, you spin around this way, and now you can kind of just move around where you're not supposed to be able to do that. So the question is it a problem with the program, right? Do these people not know how to make, a simple 2D physics engine? All right, let's let it play out. See what happens. Right? We'll see. I mean, you can see with your eyes if this thing is ever going to go back into its position. And I mean, it might. Maybe I'm wrong. It's moving to the right. Yeah, no, that's never coming back. Right? And then once I do that, so now we've got this arc, right? You can see it's increasing, right? But now once I kick this thing in, it's going to change. So it's moving this way. So now we're going to just give it an energy impulse. Right? And so now it's going to spin around its new center of mass. It has to. I do it again. Oh, I think it broke it. Yeah, it's broken. I think. No. Well, that side might be. Well, it's not too bad. Boom. I don't know if I can fix that. Houston, we have a problem. Let's see. I'm just getting sick now. There you go. There you go. Couple of good jukes that way, and then can't get that thing off of there. Houston, we're out of control. Right, and you can see we're just in an elliptical orbit now. We're not doing anything. We're like not orbit, but you know what I mean. We're just spinning around, going nowhere, which is cool. I mean, you know. All right, let's try again. Let's see if we can get this a little bit better. Okay, let's add. You know what? Let's see if we can't add a bunch more weight. Really get this thing. Ooh. Yeah, it didn't like that. It's really heavy. Boom. Boom. It's the trouble of getting that thing flying around, because that's going to be jerking us all the way around. Alright. I made that too heavy, I can tell you that right now. Oof. Maybe. Yeah, I made that too heavy. We're not going anywhere. Very cool. So much fun. Nice. Get this out of the way. I just want to see this swing around and hit the back of this thing. That's going to be interesting. Eventually. Okay. Now what happens? Okay, it's joining its speed. Now everybody's going the same speed as it whips around. See, this is gaining momentum as it comes around here, so it's going to hit harder and really crack that thing. Hit douche. See? Give it a good old whack. Yeah, it looks like the speeds are joined. I mean, this arm is kind of moving still. Alright, so let's see if we can't juke it. Oh, wrong one. Oh, wrong side. Damn it. Try again. Okay. There we go. Boom. 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 There we go. Boom. Okay. Boom. 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 Oop, nope, broken. I broke it. Maybe. Yeah, stupid thing. Pop out. Huh. It's got to be still moving. Yeah, we're good. How does it play out? Looks like we're stopped. Looks like we made it. No. No, where's it going? We're just spinning. Did I get loose? I didn't. Oop, did I? Love the way that spins. Big douche. Yeah, buddy, I don't know. Well, that's clearly broken. Yeah, I don't see us back. All right, so the trick is to save ourselves. Yeah, let's do this. Let's create a box. It should never be able to get out of. Okay, so there we go. Boom. Boom. See, I think, I don't know, I gotta figure out how to drive this thing. Boom. Skadoosh. Nice. Gotta be careful whipping that thing around because it gets stuck real easy. Alright, so power here, and then I should be able to, no, this one. Boom. There we go. Boom. Okay. Power. I missed it. We turn back around. I'm going to figure out how to drive this thing whether I... Oh, come on. Oh, shit. Broken. Broken, 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 broken. All right, try again. Oh, broken again. There we go. Nice. Love that they seed the randomness in this. So you don't always get the same thing twice. Ooh. Ooh. I like that. Look at that. Oh, you gotta be kidding me. Yeah. Come on. Come on, you're not getting back. Let's see. Let's see. So they're gonna come together. And then when this strikes here, it's going to spin this back. This is going to go up, and so this is just going to kick out. Watch. So wham, bam, thank you, ma'am. Right? So now that's going to go up. So you watch. There we go. And gadoosh. See, now we get the twisting. So, and it looks like everybody's kind of just settled in. I mean, obviously that's moving back. All right, let's kick it again. Oh. Okay. Close up, close up, close up, close up. Okay, a little bit of Duke. Oh, no, not what I wanted. There we go. I don't know, people. It looks like I might hit the stupid wall. Which I should not be able to hit that stupid wall. Because keep in mind, I made that ball pretty heavy, so this thing is going to swing around that ball. Maybe. Maybe not. Maybe it's just going to go right back into position. 8. Okay, good. Oof. And there we go. It's hard to do. I think. Oh, could be easy. Hit it again. Come around. Come around. And whack. Huh, I got it. Got the hang of it. And whack. Boom. Nope. 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 Oh, there we go. Okay. What do we do on speed? That's only let's do 100. Uh-oh. We're gonna hit the wall. You see what I'm saying? Like, there's no way we should have been able to hit that friggin' wall. Correctamundo. And I'm doing this slow and simple just so you can see how to do this. So you can make these things yourself. You can, try different, programs to see if you can elicit the same idea. But, I mean, it works. And this isn't the only thing that works. I mean, there's a bunch, okay, so look at this, guys. Right? This isn't, this guy's driving a can of pop. I mean, it's not economical. Like, that's like the worst form of propulsion. I can imagine, but it does work, and here I am. But yeah, there's a bunch of, this is, precession drive. There's a bunch of different, like this guy's here. This one's really good. Watch. You see what I'm saying? Like, whoever this person is, or wherever the hell they're at, right? They're not making this nonsense up just to try to, lie to you. They think they actually have something that no one's ever invented before, but that's not true. This has been invented a long, long time ago. Let me see. I think I still have the paper. No. I still have the paper open that I was reading. Here we go. Yeah, so this one here, this is a really good. So I was doing a search on inertial propulsion. And this, this is a research paper that's been, peer reviewed. It's a full paper, and it tells it says, okay, yeah, so we're not flying around like in Star Trek, but it has all the math for it. And like, here's a really interesting thing: these halters, I'd never heard of this before, but I'm really going to check on that because I think that's an interesting idea, where the Greeks would run and then use these to jump really far, almost like pole vaulting without a pole. I mean, this has been back, 1933. Somebody's already invented this. That's something akin to, what do you call it? The Thornton propulsion drive. This is the Dean drive. And again, the problem with these drives, it's not that they don't necessarily work. I mean, they do. But where do we go? So they do work, but you see the displacement isn't fantastic, right? And so they're just looked at as oddities. It's not like this, science doesn't know that these things are possible, right? I mean, like, watch this guy. You know what I mean? This is Cardboard Studio, right? So here, I just watch. Okay, he's a screwdriver and some cardboard to show you that this effect is realistic, right? We're not bending the laws of physics. You use the laws of physics, right? That's a ratcheting. I call that the effect of the Lewis ratchet. And the only reason I named it after me is because I actually put the math to this. So the problem that we have here is this person isn't explaining the math, right? Right? Does this work in water? Probably. If he could probably use something other than cardboard, probably. Excuse me. But yeah, so you get the idea. So I'm not critiquing what these people are doing. I'm just saying there's a bunch of people on YouTube, and this guy is fantastic, Stephen Hampton. Like, this is just nuts. This is nuts. I mean, look at this stuff. Right? 3 years ago, this guy was doing this. Right? Look, it's on water. Not Stephen Hampton. Right, he turns it on, boom, it starts shifting across the water. That's inertial propulsion. That is not supposed to be possible. That's that's inertial propulsion. There's nothing, you know, you're not breaking the laws of physics at all, right? There's many different people. So I also have the math for it if you're actually ever interested in proving or disproving this using physics and math. You could go here and read why this works. This is a simple progression, and I can't figure out how to make it with Algodo. So, but I just want to show you the layout, and I'm not going to build it because I swear I do this stuff all the time and create all kinds of nonsense. So let's go out here, and so you take a ball, boom. You take a launcher, boom, right? So the launcher shoots the ball. All right. So the launcher shoots the ball, boop, right, this way. There's a tether system, right, that has a, something to capture that ball with, and it's on an arm that spins around. So when you shoot the ball, this ball into the bucket, this whole thing spins around, right, and releases the ball this way. Where it's captured by another unit here, it does precisely the same thing. So this ball just boom, everything spins around, boom, 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 back and forth, right? And actually, the trick to it is when you shoot this in the first place, let's go back. So you shoot this ball here, what happens? Okay, so you capture, so let's assume that we just stop. So we shoot here, right, boom. Shoot here, everything stops, right? This is captured, this is captured, this is going nowhere. Okay. The problem is, if this is already spinning, let's say we spin this up, right? And this captures, and this hits this at the same speed. So we started this up, we spin it up, we put another gyro in, right? And no, not that. We set another gyro on the system opposite it, right, to offset that, make it reversed, blah, blah, blah. So this won't spin, right? And let's just draw the ship here. Bigger than that. Terrible ship. Okay, that's our ship. Boom. So this shoots out, right? Let's go here. Shoots out, boom, captured in here, gets over here, boom. Okay. So if you shoot here, right, and capture this, right, and just start spinning this around, you need to figure out the equation, right, that will dictate this system. Okay, so before you just assume that you know everything that's going to happen, right, just by looking at it, you already know this is going to blah, 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 blah. You don't really know. And that's the thing, is until you can calculate the force, the recoil force on this thing here as it's because this is one system. So this is one big platform, right? This is on a platform. This shoots that ball, right? So, and again, I understand this is completely confusing. I'm not making it any easier, but I'm just trying to explain the system of the proof. So you boom, you fire this out. This whole system gets a recoil. It's captured in this bucket. This bucket spins around. This spins opposite, making sure this whole thing doesn't spin at all. And instead of just letting it go after it spins around one time, right? What if we speeded it up and then let it go, right? So there's a difference between when we put this energy in here and we spin it up. You have to figure out what's going to happen to the system when you spin it up and let it go, right? So before you just automatically assume you know the math of it, I'm telling you, you don't, because that's where this is. This is where it explains what happens when you shoot into that system. So that's going to be on the the links. So you can go through here. Here's working models that actually work. Right? This shows you how it does it. Right? This is what I built. This is what I created as closed loop pulse propulsion. And understand, I had no idea about any of these. Like, I didn't even know the term inertial propulsion. I'd never even heard of it. That's why I invented closed loop pulse propulsion. Right? So it's not like you just know what this stuff is. Right? And by the way, so I push this away. Boom, I push it back. Anyway, you'll see. Watch the videos. So this shows you what it is. It walks you through each one of them, how it works, right? And I'm just trying to explain the dynamics. This is VPython. Again, this is not precise, but when I did my proof, I did it with this system here. So this is railguns in space, right? So you fire the railguns, boom, boom, right? And they get captured in these tether systems and then spun back and let go in this direction. So the system gets a pulse this way. And then what happens when it hits these tethers, right? If these tethers are already moving and there's no impulse, just a redirection, what happens? And again, so I'm not going to give you, I already gave you the answer. I literally wrote it down in a mathematical proof. You can see it with your own eyes. You can do it with, good God. You know, you can just look. And these aren't all mine. I didn't invent all this nonsense. These are people that are out there doing this stuff. And so it's I get the skepticism. I get why it seems like this shouldn't be doing it. And it's just because as you look at the system, it's not, you're not getting these massive, you're not flying away like they are on Star Trek because you have to build up the impulses. It's stackable. It's just like gravity. Gravity is a stackable, like you start at one velocity and just keeps adding and adding and adding and adding until you can't fall any faster. I mean, literally, you hit a terminal velocity where you're just crashing into the wind. If there was no wind, there's no terminal velocity. You're just going to smash into the ground as fast as gravity can pull you. I mean, that's just how it works. So this is the same thing. You have to start with these small little micro, hits, and that will drive you out of your frame of reference. Not your center of mass, though. That's different. Like, I know it sounds counterintuitive that the frame of reference and the center of mass isn't the same thing, but the center of mass of this system it never goes out of the center of mass. It's just you're reconfiguring the forces from each time step. So if we go back to, Noether, from one moment to the next, so I can figure out mathematically what is precisely going to happen, right? And I know that can be figured out because that's precisely what this program is doing. It's just doing the math on what's going to happen. And these sprites are just showing you the interplay. It's not magic, right? But you can see how these forces align. And is this like the most precise way of doing it? No, not at all. There's much better engines for this. There's much better ways to look at the physics, but you don't have to. This is good enough for a proof of concept. The math is done. You see it with your own eyes that it works. There's more than just me building this thing. I mean, granted, a lot of people have really high expectations for what's possible, but and some of them are just nonsense. Like I don't remotely have any idea how that's going to do anything, other than vibrate off the table. But again, so you can say like some people are making some really extravagant things. Field purple, I don't know what that. So my concept is called closed loop pulse propulsion, and it's because it uses a different mechanic. So this is using like different mechanics to achieve the same result, sort of. I mean, it's almost like it, but I built a similar model to this. These are all kind of the same linear propulsion method. So you're just going to kind of go in a straight line, and you're going to get in like little discrete hops. So you're not really like you take that out into space, and it's doubtful if you'll go, but I mean it'll be eventually, and it's just going to kind of flop all over the place. That's just this one requires gravity and friction to work, so I call that the Lewis ratchet. And if you go up here and you look at the Lewis ratchet, yeah, so this is the Lewis ratchet. So this is just tiny little shifts, asymmetrical shifts that use gravity and inertial imbalances, sort of. I mean, to simulate movement. But again, these really require friction and gravity. I mean, these don't. This is more linear closed loop pulse propulsion than the Lewis ratchet. So I didn't really know that at the time I made these videos, what it precisely I was looking at. But now that I do, it's and I tested on just a slight little shift. This is actually a good one. I recommend watching that one. But anyway, so yeah, I just wanted to kind of go over how this works again, and get a little bit more into the physics of it all. Try to explain why what you're seeing is happening. It's not we're not breaking the laws of physics here. We're actually using them and understanding them. And visually seeing what's happening. And again, you're more than welcome to attack the makers of this program and say, well, they don't know how to, model the dynamics of, I don't know, these are massive. Like, this is not a small piece of wood. So I could see where I don't know, what's the information, does it even tell you? I don't know. Oh, I can figure it out. So it's like 10 meters. It's a 10-meter plank of wood, right? So this is not using tiny little light pieces of air, and there's billions of different. I mean, some of my other things, I got a bunch of different stuff flying all over the place, and it does make you think, well, maybe it's a floating point error making it pop out, and that's just not the case. This system is very simple. You can build, and you can literally, if we go back to the one I was doing earlier, load scene, show two. So if we go back to, this model here, you forget about it. This thing is just gone, right? I turn this on, I think it's one, yeah. So turn this on and just watch what happens. Give it a minute. All self-contained, right? If I want to turn it off, turn it off. Now, what you're going to see is once everything kind of stops shuffling around, you're never putting the system back. And it's not that it can't do the math, right? It's just, watch. It's going. It's just you can't, the way that this thing is constructed is a nightmare for physics, right? Look, it's just ratcheting down now. It's still moving away. It's not spinning around. And if I want to turn it back on, right? So, this stuff is not broke. It's literally just doing the math from one moment to the next. And the math is called, it's using the Lagrangian mechanics to figure this out. So it's I mean, you can see it moving. You can just see it moving, right? And so again, you can say program doesn't work. It's got way too many variables. It's got to track two balls, a spring. I mean, this is not complicated math, people. You can do this by hand, right? So I suggest you do it by hand because this also, even though it's a really complicated way to do the, you know, do where to go, to do this math, that's essentially what it's doing. So, I urge you to kind of look at this and kind of, really just do the math before you start, assuming that, you're 100% right about, this thing not working.